Alright, this is the third video of 10th week, and in this video I'm going to illustrate how to take the derivative of exponential and logarithmic functions. So in the previous video I introduced the two transcendental functions, natural logarithm and natural exponential function. And they are presumably the best known function inverse pair and commonly used in modeling, for instance, exponential growth or exponential decay. Yeah? And in this video, we are going to study their calculus, so how to differentiate natural logarithm and exponential function. And remarkably, the functions have very simple derivatives. So for the exponential function, so for the natural exponential function, the derivative is itself. Okay, so derivative is itself. This is not a typo, so even after taking the derivative, we have the original function. It does not change at all. So the natural exponential function is the only function have this property. So it does not. It is invariant to the operator differentiation. Okay, and then the derivative of natural logarithm is going to be reciprocal. So derivative of ln x is going to be 1 over x. So we are, in this video, we are going to study why these two transcendental functions have simple derivatives and how they apply to compute the derivative of general exponential and logarithmic functions. All right, and then let me start with a natural logarithm. So function f of x is given by natural logarithm of x. So remember, this ln x is the same as log with the base e, number e of x. Okay? And the derivative of this function is reciprocal. So f prime d ln x over dx is going to be 1 over x. Okay? So I'm going to show you the proof of this. How do you get the reciprocal? But you don't have to pay much attention to this proof. The more important thing is this formula and this fact. So the derivative of a natural logarithm is the reciprocal. Okay. So the way to show this is, so I'm going to use the formal definition of the derivative. Remember, the derivative is defined as the limit of the rate of change. So as h goes to 0. So I'm going to use this definition to derive the derivative of ln x. Okay? So using this definition, I can write the derivative as limit of, because f of x plus h is ln x plus h, and f of x is ln x. All right? So that is an incremental function when we increase the argument x by h. And then I divide by h, the increment of x. And then take the limit as h goes to 0. Alright? And then here, I'm going to use the one property of a natural logarithm. So difference becomes division. So difference between two logarithms is equal to log of division. So I can rewrite the expression on the top as ln of x plus h over x. Okay, and then let me distribute x on the bottom. So this is equal to ln x over x, that is 1, and plus h over x. Okay, and then let me separate numerator and denominator. Okay, so to rewrite this limit, 1 over h times ln 1 plus h over x. Alright? And then here I'm going to use some trick, the same trick as what I used when I derived the present value of some principal k t years from now. So remember, when I computed the present future value of some principal, I evaluated this limit, but when I evaluate this limit, I did some trick. So I use this trick, divide and multiply by the same number. Okay, so I'm going to use the same trick here to rewrite this limit as so first multiply by multiply by x. So to make 1 over h be x over h, and then divide it by the same quantity 1 over x. Okay. So I multiply and divide by x. Then limit value does not change at all. So now I'm going to evaluate this limit. Okay. And for this purpose, I'm going to use one more property of natural logarithm. That is, whenever I have a power, I can bring it out and put it in front. Okay, so here x over h, suppose that I brought that out of the power and put it in front. Then I can bring it back to the position, back to the power. Right? So this limit is equal to 1 over x, limit of ln 1 plus h over x to the power of x over h. Okay, and h goes to 0. All right, finally, so if I let h go to 0, then think about this x over h. When h approaches 0, no matter what this number x, as long as this x is a positive, and remember the x is the argument of this function, and then natural logarithm, and logarithm is defined on positive interval. So this is defined for positive value of x. So x is some positive number. Okay, so when x is a positive, if we let the bottom go to 0, this quantity x over h will go to infinity, positive infinity. Okay, so taking the limit as h goes to 0 is equivalent to taking the limit as x over h go to infinity. Okay, so using this fact, I can rewrite this limit as 1 over x. Okay, limit ln 1 plus h over x. So let me relabel x over h by say t. Okay, then h over x is 1 over t, and the power x over h is t itself, and then we take the limit as t goes to infinity. Okay, once again, this limit is the same as this limit. All right, and then if we focus on the inside of a natural logarithm, our limit of this quantity, so limit of this number as t goes to infinity, that is Euler's number e. Okay, so consequently, this is a 1 over x ln e, but ln is logarithm with base e, so ln e is going to be is equal to 1. Okay, so we have 1 over x because ln e is equal to 1. Okay, So the proof is a little bit complicated, but once again, you don't have to remember this proof for the exam. So I'm not going to test whether you remember this proof. Okay? Rather, I'm going to ask you how to use this formula, the differentiation rule of natural logarithm, to compute the derivative of a general function. Okay. All right. So, but anyway, with that formula, now we can compute the derivative of any logarithmic function. So here the f of x is given by logarithm with base b of x. Okay, so this is not a so it does not have to be natural logarithm. So with arbitrary base b, now we can take the derivative of this function. Okay, and remember, log with base b of x can be converted to natural logarithm ln x over ln b. Okay, and then remember x is the variable, b is a constant. So although we have a quotient, we don't have to use the quotient rule to take the derivative because the bottom is a constant. So this is just a constant 1 over ln b times ln x. Okay, so its derivative is going to be, because this constant is multiplied, so we leave it alone. And ln x derivative is 1 over x. Alright, so the derivative of any logarithmic function is going to be reciprocal. So we have 1 over x, we still have 1 over x, and then we multiply by 1 over ln b. Okay? So for example, if we have log with the base 7 of x, then its derivative is 1 over x times 1 over ln 7. Alright, and furthermore, combining with the chain rule, now we can compute the derivative of any composite function. So composite function between natural logarithm and any arbitrary function. So remember, the chain rule tells us the derivative of composite function g of h of x is the derivative of the outer function, and leave the inner function alone, and then multiply by derivative of the inner function. Okay, so here ln f of x, that is the composite function with outer function natural logarithm and inner function f of x. So its derivative is, we first take the derivative of natural logarithm, that is the outer function. So this corresponds, ln f of x corresponds to the case when g is ln and h is f of x. So we first take the derivative of the outer function, following the chain rule. So g prime is 1 over f of x, and then multiply by the derivative of the inner function, that is f prime. So we have derivative of the inner function, f prime on the top, and f of x on the bottom. Okay? And to justify this formula, remember, natural logarithm is defined on positive interval. So this formula is applicable to positive function. F of x must be positive. If f of x is a negative, this ln function is undefined. Alright, so now using that formula, let me show you how to take the derivative. Let me go through these examples, okay, to show you how to take the derivative of natural logarithm. So we have ln 3 of ln 3x, okay, And remember, ln 3x multiplication becomes the addition. So this is equal to ln 3 some constant plus ln x. Okay? And then take the derivative. Then ln 3's derivative is 0 because that is a constant. And then ln x derivative is 1 over x. Okay? So 1 over x is the derivative of the first function. Okay? The second function, x cubed times ln x squared. Okay? First, I can bring up the power 2. So 2x cubed ln x. Okay, this 2 comes up front. Alright, and then I have the product of two functions. So using the product rule, y prime is, leave this constant 2 alone, and then take the derivative of the first function, 3x squared, and leave the second function alone, and plus constant 2, x cubed, and then multiply by the derivative of the second function. That is 1 over x. So I have 6x squared ln x plus x cubed times 1 over x. So I have to reduce down the power by 1. So 2x squared. Alright, and ln 3 over x, division becomes difference. So this is equal to ln 3 minus ln x. So its derivative should be negative 1 over x. Okay, and let me do just one more. Say this one. Okay, so now y is given by ln of ln x. Okay, so this is the composite function between two natural logarithmic functions. So the outer function is ln, and the inner function is also ln. Okay, so using the chain rule, y prime is going to be, I first take the derivative of the outer function and leave the inside function alone. So that is going to be 1 ln x. Okay, and then multiply by derivative of the inside, that is 1 over x. Okay, remember ln f of x's derivative is f prime divided by f of x. Okay, so here treating f of x, treating ln x as f of x. Okay, so I have ln x on the bottom, and then multiply by the derivative of f, so that is 1 over x. Okay, so this is the derivative of this function. Alright, and then one more application of this logarithmic differentiation. So the logarithmic function can be used to find the derivative of a complicated function in a much easier way. Okay, so think about this function x squared divided by this expression. So in order to find the dy over dx, so the derivative of this function, we have to use several rules because this is the division, so we have to start with a say quotient rule, and the bottom is given by product of two functions, so we may have to use the product rule as well. Alright, but instead there is a leeway to finding derivative, that is, we start with taking natural logarithm before differentiating. Okay, so let me take a natural logarithm of both sides. So ln y equals ln x squared over x plus 3 times 2x plus 1. Okay? Then using the property of natural logarithm, I can rewrite this, I can rewrite the right-hand side. So ln, first division becomes difference. So ln x squared minus ln of the bottom okay, and using the product rule of natural logarithm, so product becomes addition, so minus ln x plus 3 and plus ln 2x plus 1. Alright, so I can rewrite the first term using the power, so bring out this power 2, so 2 ln x, and distributing this negative sign, minus ln x plus 3 and minus ln 2x plus 1. So after taking natural logarithm, then we take the derivative, take the total differential, right? So okay, so I have ln y equals 2 ln x minus ln x plus 3 minus ln 2x plus 1. Okay. So if I take a total differential, ln y becomes 1 over y dy, and 2 ln x becomes 2 derivative of natural logarithm, that is 1 over x, and dx. And the minus ln x plus 3's differential is derivative, so minus 1 over x plus 3. So take the reciprocal and then multiply by the derivative of the inner function, that is 1. Okay, so dx. And finally the differential for the last term, that is take the reciprocal and then multiply by derivative of the inner function, that is 2. Okay, and dx. Okay, and then let me factor out dx from the right hand side. So dx 2 times 1 over x and 2x plus 1. Okay, so dy over dx, I'm looking for dy over dx. So solving for this expression, I would get y times the expression in the parentheses. All right, and the y was given by x squared over x plus 3 times 2x plus 1. So that is the derivative. That is the derivative of y with respect to x. Okay? So what about this? That is a way simpler than applying quotient and product rule. So just rather than instead of differentiating this function directly, we can find out the derivative more quickly if we take the natural logarithm before differentiating. So this process is called logarithmic differentiation. All right, and then let me explain about, so now let me explain how to take the derivative of an exponential function. So that is that is way simpler than before. So the derivative of e to the power x is itself. So e to the power x is its own derivative. So the way to show this is there are two ways. we can use implicit differentiation, or we can use the inverse function theorem. So here, so let me call this e to the power x as y. Okay, so y is e to the power x. All right, then okay, I'm looking for dy over dx. So here, if I use the implicit differentiation, so differential of y is going to be dy, and differential of the right hand side is going to be, sorry, this is an implicit differentiation, so I think, sorry, I'm a little bit confused right now. So let me take a different approach. So here, y is given by e to the power x, and then instead of implicit differentiation, let me use logarithmic differentiation. Okay, so before taking derivative, let me start with taking natural logarithm of both sides. Then y becomes ln y, and the right side becomes ln e to the power x. Okay, so once again, ln is log with the base e, so the right side boils down to x. Okay, by definition of because ln is the inverse of e to the power x. All right. Okay, so here let me now let me use implicit differentiation. So ln y's derivative differential is going to be 1 over y dy. Okay, and then x, the differential for x is going to be dx. So now I'm looking for dy over dx. So solving for dy over dx, then I obtain y, but that is just e to the power x. Okay, so once again, I defined y as e to the power x, and using logarithmic differentiation to take the derivative and solving for dy over dx, and I ended up with function y, that is e to the power x, so dy over dx does not change at all. Okay, so dy over dx is the original function. Or we can use the inverse function theorem. So if I define y as, so if I start from this relation, y is given by e to the power x. Okay, then ln y is going to be x. Okay, then if I take the derivative, both sides with respect to x using the chain rule. Wait a second, just a second. X, yeah, using the chain rule. Then I'm gonna have 1 over y, and regarding y as a function of x, then just a second. Dy over dx ln y equals x. Oh, okay. So sorry about that. So starting from ln y equals x, and let me take the derivative with respect to y. Okay, so if I take the derivative with respect to y, then the left hand side becomes 1 over y, and the right side becomes dx over dy. Okay, so that is the derivative of the inverse, so the derivative of x with respect to y. So dy over dx, oh yeah, that was the implication of the inverse function theorem. So derivative of the inverse is a reciprocal of the original function. So we found the derivative of the inverse, so dx over dy, that is 1 over y. So the derivative of the original function is going to be y. So that is e to the power x. Okay. So either way, we obtain this starting conclusion. So the derivative of the exponential function, natural exponential function, is itself. Okay. So using that formula, we can compute the derivative of any exponential function. So when base is given by some constant b, okay, the way to find out the derivative is, remember, we can convert this b to the power x to natural exponential function. So b to the power x is equal to e to the power x ln b. Okay? Then we are using the chain rule, we can find the derivative. So its derivative is, because this is the composite function, outer function is natural exponential function e to the power x, and inner function is x times ln b. Okay? And then the derivative of the outer function is itself, it does not change at all. So it's going to be e to the power x ln b. And then we multiply by derivative of the inner function. So the derivative of the power, that is ln b. Okay? So after taking the derivative, we have ex ln b, but that is identical with b to the power x. So we obtain b to the power x ln b. So I think this is a typo. It should be b. So b to the power x rather than e. Alright, so for example, how to take the derivative of, say, 3 to the power x. So we rewrite this function, 3 to the power x, and then multiply by ln 3. Okay, so that is the derivative. So when base is equal to e, we can do the same job. The derivative is, we rewrite this function, and then multiply by ln e, but ln e is equal to 1, so we have the, we can draw the same conclusion that the derivative of natural exponential function is itself. Okay? And then let me illustrate this point in the live lecture. This is very important. So there is an alternative way to define number e. Okay? So e is the unique positive number base b such that exponential function has a slope of 1 at 0. Okay? But let me illustrate that. Let me illustrate this point at the live lecture this Friday or next Friday. Okay? And combining with the chain rule, now we can take the derivative of this type of function. So e to the power h of x. Okay? I already showed one example here because I treated this e to the power x ln b as a composite function to find the derivative. Okay? But whenever we have a function h of x in the position of in place of exponent, then the way to find the derivative is we first rewrite the function, so e to the power h of x, and then multiply by the derivative of the power, h prime. Okay? So for example, we have e to the power 5 minus 7x. Okay? Some function of x in the position of exponent. And then the way to find the derivative is so y prime is, we rewrite this function and then multiply by the derivative of the power, negative 7. Okay? E to the power negative 5x, that is the same. Y prime is e to the power negative 5x, and multiply by derivative of the power, that is negative 5. Okay? we have an exponential of this expression. Remember, this is the same as e to the power, alternative expression of natural exponential function. So the derivative of this is, we rewrite the function and then multiply by the derivative of the power. So x squared first becomes 2x, and the derivative of a square root of x is, this is easy, so it is useful to remember this formula. Square root of x derivative is 1 over 2 square root of x. So we have 4, constant 4, so 2 over square root of x. Okay, and let me show you just one more formula, one more exercise. So let me go through one more exercise. Say this one. Okay, then y is given by natural logarithm of e to the power x over 1 plus e to the power x. So let me first use the property of natural logarithm to rewrite the function. To remember, division becomes the difference. So ln e to the power x minus ln 1 plus e to the power x. But the first term, because a natural logarithm is the inverse of exponential function, natural exponential function. So the first term boils down to x. Okay? And then we can simplify the second term. So leave it alone. And then we take the derivative. So its derivative is x becomes 1. And then derivative of a natural logarithm. So we take the reciprocal of the inner function and then multiply by the derivative of the inner function. So 1 goes away, this 1 goes away, and e to the power x's derivative is itself. Okay, so that is the derivative of the last exercise. Alright, so in this video I explained how to take the derivative of two transcendental functions, and hope you guys found this video useful, and I'll see you guys in the live lecture this Friday.